We are in section 5.4, applying definite integration, distribution of wealth, and average values. The first box that we have here, we're going to go ahead and star. This is the total area between a curve and the x-intercept. This is going to be a positive area when the function is greater than 0 for the interval, and a negative area when the function is less than 0 for the interval. So you can see our positive area is above our x-axis, and our negative is going to be below. And it says the x-intercept is where the area will change from positive to negative. And so to figure out our total area, we are going to take our positive area and we're going to subtract away, so minus our negative area. So what that would do is change that negative to a positive, and we would get our total area. And again, remember to find your x-intercepts. This is where you set y equal to 0 and you would solve. And so that you can see at that x-intercept where y is 0, and in this picture it's at 3, is where it changes from having a positive area to a negative area. So right below this it says finding area. In summary, to find the area bounded by f of x from a to b and the x-axis, use the following steps. First is going to be to sketch the graph of f of x. 2 is to find any x-intercepts on that closed interval. Then divide these total regions into subregions. The definite integral will be a positive for subregions above the x-axis and negative for subregions below the x-axis. Use separate integrals to find the positive areas for each subregion. The total area is the sum of all the areas in the subregion. So adding those all up, again, those negatives, you want to subtract them away, which would make it become a positive value that we are discussing. So on the next page, top of page 12, says use the definite integral to find the area between the x-axis and f of x over the indicated interval. Check first to see if the graph crosses the x-axis and the given interval. So the first problem that we have is f of x equals 4x minus 32 on the interval from 5 to 10. And so if we were to graph this function that we have, again, just kind of having a rough sketch of this, we're going to be going from 5, so starting at 5, all the way out till 10. So I'm going to label this 5 over here, and then all the way out till 10. And when you substitute in 10 into your function, you have 4 times 10 minus 32, which is 8. So I'm just going to go ahead and label this as an 8 up above, putting a dot. And then when you substitute in 5, you have 4 times 5 minus 32, and we arrive at a negative 12. Again, you can draw this to scale a little bit better, but if you notice, it does cross the x-axis somewhere in here. So I'm able to find my x-intercept by taking my function, which is 4x minus 32, and that is equal to y, and setting it equal to 0. When I solve this, I'm going to arrive at x is equal to 8. And so this crosses at 8. And so I have two areas. I have one that's going to be above, and this is a positive area, and then one that's going to be below, which is my negative area. So in order to find the area, I'm going to be integrating this, and I'm going to take my positive area, which is going to go from 8 till 10, of my function, which is 4x minus 32. Do not forget your dx. And I'm going to subtract away the negative area, the one that's below the x-axis, which is going to be the integral, and this time we're going from 5 until 8 of that same function, 4x minus 32 dx. Integrating this function, we arrive at 2x squared minus 32x. And we are going to evaluate the first integral from x equals 8 till 10, minus integrating the second integral, which again that is going to be the same function, 2x squared minus 32x, and then evaluating this from 5 till 8. So evaluating this at 10, we're going to have 2 times 10 squared minus 32 times 10, and we arrive at negative 120, minus, evaluating this at 8, 2 times 8 squared minus 32 times 8, just go ahead and use your calculator for that, and we get minus negative 128. And so this first function here, we can simplify a little bit more, but let's go ahead and subtract. Evaluating this at 8, we have minus, we're going to have that negative 128, which we just did, minus, evaluating this at 5, and have 2 times 5 squared minus 32 times 5, we have negative 110. Simplifying that first set of parentheses here that we have, we arrive at 8 minus, and then we have negative 128 plus 110, it's going to become 18, and it would be negative, and then this would work out to being 26. So again, this is our area that we are calculating. So part B, the next one that we have, is an integral that we're going to have to set up, and our interval is going from 0 to 6. So this time when I draw my graph to get an idea of what's going on with this, I'm going to be going from 0 to 6. So 1, 2, 3, 4, 5, and 6. And if you were to substitute in 0, you have 9. So I will go ahead and mark that up here. This is a parabola. And we have, when you substitute in 6, you have 9 minus 6 squared, which works out to be negative 27. And again, you can definitely make a t-table and draw this a little bit more accurately than what I am doing here. But if you draw your parabola, it should look something like this. And this is between, when you talk about areas, it's always between the x-axis and the graph, and that value on the left and right sides. So we have our first area up here, which is definitely a positive area with it being above. And then our second area, which is down here, which is a negative area and is below. So we need to first find our x-intercept. And to do that, we take our function and set it equal to 0. When we do, we get x squared is equal to 9, or x is equal to plus or minus 3. But since we are only dealing with the interval from 0 to 6, the only x-intercept we have is at positive 3. So I'll put a point right there. That's going to be what's separating our two integrals. And so we're going to take our positive integral, which is going to go from 0 to 3, of 9 minus x squared dx, minus the negative integral, which is going from 3 to 6, of 9 minus x squared dx. And when we do this, and we integrate, we have 9x minus 1/3 x cubed, evaluated from x equals 0 to 3, minus, integrating again that second one, we arrive at the same function, 9x minus 1/3 x cubed, evaluated from x equals, and we're going from 3 to 6. And then when we evaluate the first one, we substitute in 3, and as we substitute in 3, we get out 18. So make sure to try that on your own. 9 times 3 minus 1/3 times 3 cubed, minus, substituting in 0, it's just 0, minus, and then substituting in our upper bound here, which is 6. 9 times 6 minus 1/3 times 6 to the 3rd power, we get negative 18. Minus, and then substituting in 3, we get 18. Working this out, we end up with 18 minus negative 36, which works out to being 54. The next example that we have says a small company found that its rate of profit in thousands of dollars after T years of operation is given by, I want you guys to notice we are dealing with a profit function. However, it's not the function, it is the derivative, it is the rate of profit. And it says part A says to find the total profit for the first 3 years. So in order to do that, I need to integrate my profit function. And so I'm going to integrate this. Our profit function is t plus 1 times t squared plus 2t plus 3 raised to the t raised to the 1/3 power. And my limits of integration, put your dt there, are going to be for the first 3 years. So that would be going from 0 to 3. And with this, I notice that I cannot integrate this as it is written. So I'm going to have to use either u sub or integration by parts. So always try u substitution first. So if we were to use u substitution first, I would let u equal that inside function, which is going to be t squared plus 2t plus 3. And then du, taking the derivative, would be 2t plus 2, which is the same thing as factoring out a 2 and having du is equal to 2 times t plus 1. And I'm going to go ahead and put my dt in here also. So I can say that dt is equal to du divided by 2 times t plus 1. And so from here, I'm going to go ahead and say this is equal to, and I'm going to put my limits of integration on in just a sec, but I have t plus 1 times u to the 1/3 times dt, which is the same thing as du, divided by 2 times t plus 1. So the t plus 1s would reduce out, and I would have the integral of 1/2 u to the 1/3 du, and again you can put that 1/2 out in front. However, I have not written my limits of integration yet, and the reason why is they're not 0 to 3 because I changed my limits. So I need to substitute into this 3. So I have 3 squared plus 2 times 3 plus 3. And when I substitute this in, I get a value of 18. So that would be my upper limit of integration with respect to u. And then my lower limit of integration, I'm going to substitute in 0. So 0 squared plus 2 times 0 plus 3. So that works out to being 3. So I'm going to be integrating from my lower limit of 3 to my upper limit, which is 18. When I integrate this, I end up with 1/2 times adding 1 to my exponent. I have u to the 4/3, and I multiply by the reciprocal of that out in front. Again, we do not need to put a plus c because it is a definite integral, and we're evaluating this from u equals 3 to 18. So simplifying this, I have 3 over 8, and it's going to be 18 to the 4/3 minus 3 over 8 times 3 to the 4/3. And if I substitute this into my calculator, I end up with 16.067. And the units that we have are in thousands of dollars. So put down thousands of dollars. And again, you can leave your answer like this. However, another way to do that would be multiplying by 1,000 and rewriting this as $16,067. So either of those, their equivalent answers would work. The problem does continue on to the next page, and this one says find the profit in the 4th year of operation. So finding the profit for the 4th year, I would be integrating this. Since it's only the 4th year, that I'd be going from 3 to 4 of my function, which was t plus 1 times t squared plus 2t plus 3 dt. And I can go through the whole work of letting this be u and figuring everything out. However, what I'm going to do instead is I'm going to go ahead and rewrite this using what we had already done in part A. And I know that, so I'll put some dot dot dot, so if you need to rework it out yourself, you definitely can. And so for this, my function simplifies to it's 3 over 8 u to the 4/3. And again, I need to deal with my limits of integration here. I can evaluate this at my new limits of integration, but I don't know what they are, so I'd have to change those. Another way to do this would be to back sub in what u was. And remember, u was equal to t squared plus 2t plus 3. So I can back sub this in, and I add 3 over 8 times t squared plus 2t plus 3 raised to the 4/3 power. And since we're back in our t variable, I can say this integrates from 3 to 4. When we do this, we have, I'll put down dot, dot, dots, work out all the work there, and you should arrive at 12.685, and it's thousand of dollars. And again, you guys can leave it as this or multiply by the 1,000 and you end up with $12,685. So either one of those is correct. Part C says, what is happening to the annual profit over the long run? And so if you look at these two, this first one, part A, was our first 3 years, and this was just that 4th year of operation. So that is definitely increasing. So I'll put down, it is increasing. So the next box that we have down here, we are going to go ahead and star. And this is the area between two curves, rather than between the curve and the x-axis. So it says if f of x is greater than g of x on the interval from a to b, then the area between the curves f of x and g of x from a equals x to b equals x is given by, and I want you guys to notice it's the upper equation minus the lower equation. And that's always going to be it. So to figure out that region of it in between, like you can see on the picture, you are going to take the area of the region under f, which again, f is this top function, which would be all of this. And then we're going to subtract away the area of the region under g, which is that lower. And when you take that total area minus that bottom area, you get the area between the two curves, and you can see that in the picture. So it is written there for you guys with formulas also. So the example right below this says, find the area bounded by f of x equals 4 minus x squared and g of x equals x plus 2 from x equals -2 and x equals 1. So the first thing I'm going to do is graph this. I think graphing helps students out so much because it allows you to visualize it. I want you guys to notice too, it says that we are going between -2 and 1. Sometimes it does not give you those values and you would have to figure out where the two graphs intersect. So for this one, we are going to be going from -2 to +1. So I'm going to go ahead and sketch my graph. So sketching my graph, it's going to go from to +1. And so at -2, if I were to graph that first equation here, substituting in -2, I would end up with 4 minus 4, which is 0. And then I would substitute in -1, so 4 minus +1 would be 3. And then substituting in 0, I get 4. And then substituting in 1, we're back down at 3. So there's that graph. I'm going to go ahead and label this so I know which one I'm talking about. That is f of x. The second graph that we have is g of x, and that is just a straight line. So if you have it -2 would be 0 if you substitute that in. 1, -1 plus 2 is +1. Substituting 0, we get 2. And then substituting in 1, we arrive at 3. So we have our straight line right here. So this is going to be g of x. Go ahead and labeling that. So our function here is going to be, this is my upper, and this one is my lower. So this is upper and lower on the interval. And again, we're only talking about the interval from 2 to 1. So my integral is going to be going from -2 to +1 of, and I'm going to take my upper function, which is f of x, which is 4 minus x squared, and subtract the bottom function, which is g of x, which is x plus 2. Again, making sure to put the functions in parentheses because that negative needs to be distributed to the whole function, and then not forgetting our dx. So this is going to simplify to go from -2 to +1 of, and simplifying our function, we have -x squared minus x plus 2 dx. And then integrating this, we end up with negative 1/3 x to the third minus 1/2 x squared plus, then we have 2x. And this is going to be evaluated from x equals -2 to +1. So from here, evaluating our antiderivative at 1, we arrive at 7/6 minus, and then evaluating our antiderivative at -2, we arrive at -10 divided by 3. And so 7/6 plus 10/3 is going to equal 9/2. Again, you can also write this as a decimal, and that would be completely fine also. So the next example on the next page, we are going to go ahead and circle, and we will work on that one together in class. The next thing that we have is the net excess profit. Suppose one investment will generate a profit of P1T, and a second investment will generate a profit of P2T. The derivatives of each of these profit functions is then respective rates of probabilities. If the derivative of P2T is greater than the derivative of P1 of T over the next n years, then E of T is equal to P2T minus P1T, represents the excess profit of plan 2 over plan 1 at time T. Then net excess profit would be NE equals E of N minus E of 0. You can see that in the graph on the right. That's the same one from our textbook. And so to calculate NE, or our net excess profit, we have an equation right here, which is going to be an integral, and it's going from 0 to n for the years that we have of our E prime of t dt, or again taking that of each of those plans individually and subtracting the second plan over the first. So the first example that we have says, suppose that t years from now, one investment will be generated profit at a rate of P1 prime of t equals 50 plus t squared, $100 per year, while a second investment will generate profit at the rate of P2 prime plus 200 plus 5t, $100 per year. For how much years does the rate of profitability of the second investment exceed that of the first? So first of all, it wants us to figure out for how many years does the rate of profitability of the second investment exceed that of the first. So in order to do this, we need to figure out where they are. Second investment exceeds that of the first. So we can go ahead and say P1 prime of t would be less than P2 prime of t. And so in order to solve this, P1 is going to be 50 plus t squared, less than 200 plus 5t, which is our second profitability function. Solving this, I'm going to move everything over to one side, and we have t squared minus 5t minus 150 is going to be less than 0. Factoring this, we end up with t plus 10, and then t minus 15, which is less than 0. Solving this, the first one that we would have, and you can set up a number line here, which again needs to go from 0 and on. You'll notice that solving this and setting this equal to 0 before figuring out which intervals are increasing and decreasing, setting this equal to 0 and solving this, we would have our values be at t equals -10 and at positive 15. So we only have to worry about positive 15 because -10 does not make sense with time. So going ahead and looking at this, that means that substituting this in and figuring out where it is less than, and so we can see that substituting in the first one would be where it would be negative or less than 0. Anything larger than 50 is going to be positive or greater than 0. And so with that said, this is going to be where the second investment exceeds the first. And so in ours is going to be where it was less than 0 is what it was asking for down here. And so since we're asking that, it would be for the first 15 years. and then after that it switches, and that first investment becomes more profitable. Part B says to compute the net excess profit for the time period determined in Part A. Interpret the net excess profit as an area. So the first thing we need to do is to compute the net excess profit. So in order to do that, we need to come up with our equation, which is going to be E of t, which is going to be our profit 2 of t minus P1 of t, or taking the derivatives of each of these, we can put those in. And this time period that we're dealing with is over time from 0 to 15, which is what we saw in the previous problem. So NE, from the formulas up above, is going to be E of 15 minus E of 0, which is equal to the integral from 0 to 15, using our fundamental theorem, of E prime of t dt. And again, remember our E we had before taking our derivatives. And so from here, we can integrate this, and we are going to arrive at the integral from 0 to 15 of P prime of 2t, which is going to be 200 plus 5t minus 50 plus t squared, which was our first function, and then dt with respect to t. Simplifying this, we have the integral from 0 to 15 of 150 plus 5t minus t squared dt. And then integrating this, we have 150t plus 5 over 2t squared minus 1/3 t cubed, evaluating this whole thing from t equals 0 to 15, and substituting in 15, and then substituting in 0 and subtracting those two, we end up with, I'm going to write it as in decimal form, 1687.50, and what we are dealing with here is going to be our net excess profit. This is in our problem is dealing with hundreds of dollars. We can also multiply this by 100, and we end up with the same amount, just written a little different. So 168,750, and this would be our excess profit. And this is the area between profitability. So it says interpret the net excess profit as an area. And this is the area that's between our two functions, that area between the profitability. The next thing that we have is the average value of n numbers, and you know about finding averages or the mean, and it involves adding up all those numbers and dividing by however many there are. And so the average value of a function f on an interval from a to b can be defined in a similar manner. Divide the interval ab into n subintervals, each with a width of delta x. Then choose an x value, x sub I, in each interval and find f of x sub I. The average function value for the n subintervals is given by adding up all those f values and dividing by n. Since b minus a divided by n is delta x, taking that interval and separating it, we did that when we talked about area, we can work this out and finding our average and rewriting this, we arrive at now taking the limit, and we arrive at a function which is defined by our average value of a function. Let f of x be a function that is continuous. So this only works if it's continuous on the interval a to b. Then the average value v of the function f of x over the interval is defined by 1 over b minus a, the integral from a to b f of x dx. There is a graph of what we are talking about right below. This says the rectangle has the same area as the shaded region under the curve. So this is found by the height of the horizontal line is the average value of the function, which is what we are calculating. On the next page, it says find the average value of the function f of x equals 2 minus 3x squared on the interval from a to b, and a is 1 and b is 3 in this problem. So our function is going to be 1 over b minus a, so 3 minus 1, the integral from 1 to 3 of our function, which is 2 minus 3x squared, and then dx. So integrating this, we have 1/2 the integral from 1 to 3 of 2 minus 3x squared dx. So now actually taking that integral, keeping that 1/2 out in front since that is a constant value, we arrive at 2x minus 1/3 times 1/3 x cubed. 3's are going to reduce out, and we are evaluating this from x equals 1 to 3. So from here, we are going to substitute in 3, and we have 1/2 times 2 times 3 is 6, minus 3 to the third, which is going to be 27, minus 1/2, and then evaluating this at 1. And so we have 2 minus, evaluating that at 1 is just 1. Simplifying this and working this all out, we arrive at an average value of negative 11. The next example that we have says find the average value of the function. Our function this time is f of x equals x plus the square root of x on the interval from a is 1 to b is 4. So again, going through this, we have 1 over, it's 4 minus 1, times the integral from 1 to 4 of our function, which is x plus, and I'm going to rewrite this as x to the 1/2 dx. Same thing, it just makes it a little bit easier to integrate. So we have 1/3 times the integral of 1 to 4 of x plus x to the 1/2 dx. And then we have 1/3, which is our constant, 1/2 x squared, plus, adding 1 to my exponent, we end up with 3 over 2, multiplied by that reciprocal out in front, evaluated from x equals 1 to 4. And from here, I'm going to substitute in 4, and then substitute in 1. And when we do, see if you can work that out on your own, we end up with 73 over 18. So the next example is an application of this. So this says a company determines that its weekly online sales, S of T, in hundreds of dollars, so keep that in mind, hundreds of dollars, T weeks after online sales begin, can be estimated by S of T equals 9e to the T. Find the average weekly sales for the first 5 weeks. And so since we're talking the first 5 weeks, that know that our interval is going to be going from 0 to 5 after the online sales begin. And so it does say the word average, which is a good indicator that we need to find the average value. So my average value formula is 1 over b minus a. Okay, our interval is given the first 5 weeks. So we have 1 over 5 minus 0. The integral from 0 to 5 of our function, which is 9e to the t, and then integrating with respect to t. This is going to be 1 over 5 times the integral from 0 to 5 of 9e to the t dt. The 9 is able to come out in front, and then the integral, the antiderivative of e to the t is just e to the t, going from 0 to 5. And then evaluating this and subtracting around the lower, we get a value, substituting this into our calculator, of 265.3437. And this is in hundreds of dollars. So we can multiply this by 100, and you can also write this as 26534.37, and so that would be an equivalent answer. So we have another example that's on the next page, and we are going to go ahead and circle that one and work on that one together in class. Section 5.5 is additional applications of integration to business and economics. We discussed equilibrium price in previous chapters. We will now use equilibrium price to discuss the idea of how consumers and producers' supplies work. So we have equilibrium price is the price of a good where the supply is equal to the demand. So S of Q is equal to D of Q, or we can also call it P naught. The market determines the price at which a product is sold. The consumers will produce the same amount of a product that the manufacturer wants to sell at the equilibrium price. Some consumers, however, would be willing to spend more for an item than the equilibrium price. The total of the difference between the equilibrium price for the item and the higher price the individual is willing to pay is thought as savings realized by those individuals and called the consumer's surplus. So consumer surplus is defined as the difference between the amount the producer is willing to supply goods for and the actual amount received by him when he makes the trade. So we're going to star the box right below, which is our consumer surplus. And this says if Q naught units of a commodity are sold at a price of P naught dollars per unit and P is equal to D of Q, is the consumer's demand of the function for the commodity, then the consumer's surplus CS is given by the integral from 0 to Q naught of dQ dQ minus P naught Q naught. CS is the total amount consumers are willing to spend for Q naught units minus actual consumer expenditures for Q naught goods. Similarly, if some manufacturers are willing to supply a product at a price lower than the equilibrium price, the total difference between the equilibrium price and the lower price at which the manufacturers would sell the product is considered added income for the manufacturers and is called a producer surplus. So producer surplus is defined as the difference between the amount the producer is willing to supply goods for and the actual amount received by him when he makes the trade. And so we have right below that a box that's for our producer surplus. It says if Q naught units of a commodity are sold at the price P naught dollars per unit and P naught is equal to SQ is the supply function for the commodity, then the producer surplus PS is given by P naught times Q naught minus the integral from 0 to Q naught of S of Q dQ. And you can see in the graph right below this where we actually have our consumer surplus and our producer surplus and where the equilibrium point is. Right below this, we have another example that we are going to go ahead and circle, and we'll work on that one together in class.